Just want to say thank you very much for joining my session today. We're going to be talking about failures a little bit. So I hope everybody gets relaxed. We're not going to be stressed. I think during the session it's okay if we fail something, but maybe not the demo. I'm going to start by asking how many of you in the audience have started or are playing with microservices right now? Okay. Now, another tough question. How many of you have had failures so far? Going to raise a big hand. OK, I'm not the only one. It's nice, right? It's nice when you have failures and live after the failures and tell the stories. That's what the sailors say. It's fine if you have an issue with the boat, but if you manage to live afterwards and tell the story, that's great. So then you kind of agree with my what I want to say here, that if we didn't fail with microservice at least once, it means we didn't really try anything new, like a new deployment or a new pattern, or just something new in the application. Microservice architectures comes from this evolutionary design in which application developers find themselves pushing the systems to new limits. And in this architecture, we typically decompose a bigger service into smaller pieces called microservices in order to compose them back and form what we believe to be a more powerful system. But one of the laws of the fifth discipline, if you read the book of Henri de Haut, he's a Dutch business executive, says that the harder you push a system, the harder the system pushes back. So this is true for a microservice environment, especially when the system is not ready to meet the demand. Sometimes this may be caused by a higher volume of traffic than the system can serve. There may be other cases as well. And at that point, when the demand is bigger than what we can serve, if we push the system, failure is almost inevitable. And we see things like this, or like this, or even like this. I like this one from GitHub, or any classic one. Some reasons for failures could be a client that misbehaves, an application that has a bug or an issue, and suddenly it's being distributed to millions of users, and it starts to put pressure onto a system. It could be a spike in demand, a legitimate spike. It could be a distributed denial of service, or a failure in one component, or a failure in one microservice that is somehow generating a cascading effect in other microservices because some retries mechanism and things like that, or clients keep on retrying. So same as in health, because prevention is usually a much better option than curing, my presentation today is going to focus on preventing some of these from happening. And in particular, I'm going to talk about traffic management with nginx. Share the story, do a demo, share what we did so far, share some of the open source projects that we maintain, and hopefully you'll be able to use, or you'll find that what we did may fit some of your use cases as well. So our story, we started with what nginx is offering by default. So we have the HTTP limit request module. You might be familiar with it. In this, we can limit the rate of the request. We can define a request zone. Let's see if I can put my cursor over there. No, you don't see my mouse. So we can define a request zone. In this case, I'm limiting by the remote address. I'm defining two zones. There's a gold and a silver zone, and I give each other like 330 requests per minute. And then I go and I define a location, and I say, for this location, I want you to use the the zone silver, and I'm allowing a burst of 5. Besides limiting the rate of the request, we can also limit the number of connections. There is another directive in nginx, and this example shows a limit to maximum 10 connections for each client IP address. This is all great, it's wonderful. In our setup, However, we have multiple nginx boxes, and they live in a tier, which for this presentation you could imagine as being like the load balancer tier. And then the microservices are deployed in a different tier, which could be the microservice tier. You could even move further and imagine that the nginx, the load balancer tier, is the only one exposed publicly, and the microservices are only exposed internally. So the only way in is through the nginx nodes. So the problem in such a setup is, if I want to limit the service to 10 requests per minute and I have 2 nodes, how would I do that? And what happens when a new node comes up or even goes away? If I set up a limit per node and my number of nginx nodes is variable, then how will I be able to predict exactly how many requests will my service be limited at? So we looked at this module. So the pros is that it's easy to configure, it was easy to manage, works really great for a single node. The cons is that when you want to define rules across the cluster, there are some problems. And there's also something dynamic that we needed to do. For instance, allow for that same location, instead of having like a single zone called silver or gold and just fit everybody into that, be a little bit more dynamic and give different applications different limits. So because this module didn't work, we started to build a distributed solution in nginx. As requirements, we wanted to work in a distributed environment. We wanted to make it asynchronous and try to not add any latency to the request. Highly performant, be able to sustain hundreds of thousands of requests per second. Adaptive, be aware of the fact that the instances of nginx may go down and up and down, so the number is variable. And fail-safe. We wanted that whatever we do, whatever solution we come up with, if it doesn't function at some moment in time, then just allow all the traffic instead of just like blocking everything. As assumptions that we made was that the service team's intent is rather to allow traffic than to block. So the focus is more on ensuring a fair usage policy. If I'm provisioned with 1,000 requests per second, I just want to give each application that uses like a fair usage policy. And then the second important assumption is that we wanted to favor performance instead of precision. So we assumed that service teams would be okay, like if they say they want to limit at 2,000 per second, that if we go 2% or 5% over, it's going to be okay with this implementation. But the request time is not going to be impacted at all. That's what we've been targeting. We wanted to keep, if possible, to 0 sub-millisecond, so less than 1 millisecond latency added to the request by just checking rules. The challenges that we face is, how do you maintain distributed counters across a cluster, right? In nginx, if you have a single node, you can maintain those clusters in a single node. But if you have a cluster of nodes, then how do you maintain that? And also how to make it asynchronous and non-blocking. So the first option we analyzed was, if we have 2 nginx nodes and each node keeps its own counters, how do have each node inform each other about their counters and have like a message exchange between the nodes? With 2 nodes, it looks okay. With 3 nodes, we were adding more traffic and more messages. So the challenge was that this solution is a little bit chatty. The more nodes you have, more messages. Maintaining a consistent distributed counter in a cluster is not an easy problem. We looked at how Cassandra is doing, and it's not that easy to maintain it. And we also did, like, this option also increases the nginx complexity because we have to put all this logic inside of it. And sometimes when we have to update it, there's a maintenance overhead there that you have to update it. If you have new rules, how do you add those rules into nginx? How do you activate them? The second option we looked at was to try to move something out of nginx and keep nginx as light as possible and try to move some things out into some different layers. So we started with the 2 nginx nodes. And we imagine how would it be if nginx would send the usage data into a broker message queue. So every single request that goes into nginx is being logged into a message queue, from which another microservice called tracking microservice consumes these messages, has like a business rules inside, and then makes decisions on behalf of nginx of what needs to be blocked or not. And for instance, if it finds out that an application needs to be blocked for 100 milliseconds, we'll send messages back to each nginx nodes with what to block, or sometimes slow down or delay. So this option, when we looked at this option, some of the challenges we faced was that we had to maintain a brokered message queue. And the question is, do we need one? Do we want to maintain an extra broker message queue for this? The other challenge is to maintain a new microservice just to track these counters and implement these rules. It's not, one thing is to deploy an nginx nodes, and the other thing is to have a queue plus a microservice. However, the improvements that we saw is that this solution is less chatty because the node is only communicating into one single message broker, each log. And then we moved some of the problems from nginx into a microservice. So we were able to keep the nginx lighter. That's something that we wanted, because one of the assumptions was anyway that in case this solution doesn't function, the traffic is permitted. So in case the message queue goes down and the tracking microservice goes down, in the worst case scenario, all the traffic will be permitted until these two services are being brought back. However, there were these challenges. So we looked at a third option. Third option, which meant to put a message queue inside nginx somehow and still keep like the same principle. Like instead of having one broker message queue, put the queue into nginx and have the same microservice pulling from that queue and also crunching the usage data and notify the nodes back if something needs to be blocked or slowed down. The challenges with this problem is how to embed the message queue in nginx, how to maintaining a new microservice to track those counters. And at this point in time, because the message queue stays with the nginx nodes, we have to have a way to discover the nodes. Like if a new node comes up, the microservice needs to find out about it to know. Also, the improvements were that in this option, number 3, we removed the broker message queue. And same as in option 2, we actually managed to move away from the maintaining a distributed counters across nginx nodes. So in 2013, when we implemented this option number 3 seemed like a good option to go ahead with. The next thing that we looked at was, okay, if we put a message queue, which message queue should that be? We looked at a few of them. Looked at the language that they're built and so look at the pros and cons. Not sure how big it is all the way to the back, but I'm just going to quickly describe our decision process. So we first looked at Kafka, of course, very popular, very performant, is known to sustain 2 million messages per second, it's not a problem. As a cons is that it's zookeeper dependent. Yet another dependency to maintain. It's a little bit more complicated to maintain it, and it was brokered, so we said we don't really need the brokered message queue. We went ahead and we found out like ActiveMQ and RabbitMQ, they're also brokered, so we said, let's try for the first version to stay away from it. Then we looked at the Nano message, which is a performance socket library. It promises a cleaner API than ZeroMQ. And then lastly, we looked at ZeroMQ, which is around since 2007. We knew it's stable, it's behaving okay. It's embeddable in nginx because it has those C++ law bindings. Basically, if you're not familiar with ZeroMQ, it's like the way I perceive it is more like a wrapper around socket. It gives you some nice APIs around it. At that time, we said, let's try to go ahead and move with option 3 and ZeroMQ. So this is the option that we moved ahead with the message queue, with a microservice for the business rules. And the integration of ZeroMQ in nginx was not as straightforward as we have imagined. Initially, we thought that we can put the 0MQ into the nginx master process. So when nginx starts, we start a 0MQ socket. And then that's not actually possible in the master process, because the master process is supposed to only take care of starting and reloading the nginx workers. So that didn't work. Then the other option that we did is we said we're going to create like a companion process for nginx. The same way that we saw at the keynote the agent that runs on the machines to send usage data. This is a similar thing. So we created a very simple process. We call it 0MQ adapter process, and it opens for nginx. It communicates with nginx via IPC, so that we don't use sockets, TCP ports. And with the outside world, we opened a TCP port on a specific port so that the microservice can actually consume the message. And then when it communicates back with the nginx worker, it will just go over HTTP. But the nice thing with the 0MQ idea is that it's asynchronous, it doesn't add latency, and we can actually forward all of the logs through it. As the integration, we use the Lua FFI for a function interface. And I'm not sure if you're familiar with the Lua module for nginx. It's pretty nice. It's easy to add logic inside of nginx. So we defined with FFI, you basically define the things from the C headers, and then you can call the API directly. If you see these 3 lines here that I've added is how nginx sends a message to the 0MQ. That's it. These modules are also into the open source. I've added for your reference. You can download my slides, and you'll find them here. It's a 0MQ adapter and the 0MQ logger. The tracking microservice is still in the works. I wanted to make it ready, but with legal, I didn't manage to finish that. We'll be publishing that one soon as well. But so far, only these 2 projects are in the open source with 0MQ. Now let's talk a bit about the nginx and the tracking service. You know, in the responsibility, the tracking service is the one that persists the policies. nginx only enforces the policies. The tracking service sends actions to the gateway based on what it needs to be tracked and the policies. And nginx is pretty, I should say, blunt, because it just knows about a set of actions, like there's an action called track. Track is starting to log things to the microservice, or block, or delay. The tracking service is concerned with the business rules, managing throttling and rate limiting, and can be updated independently. And nginx is unaware of those business rules. The tracking service is private, nginx can be public. As the request flow, there is a client that calls into the gateway. We use nginx as the API gateway. Then goes to the tracking microservice. Oh, sorry, not the tracking microservice. It goes to a microservice itself in the back. The response is sent back to the client. Then in the log phase, if you're familiar with the nginx phases, in the log phase, it sends a message to the 0MQ, which is pulled by the gateway tracking service. And in case something needs to be blocked, the gateway tracking service, we call it GTS because it's fast, sends some messages back into the gateway. Only when something needs to be blocked or delayed. So I'm also listing some of the APIs for the GTS and the gateway. Some of the folks in the back, this may not be so visible, but I posted here for reference. There is a REST API that we're going to play with today in the tracking service on how to add policies. And then once a policy is added into the tracking service, the tracking service will start telling the gateways, I'm interested in this kind of requests. For instance, I want to know all the requests for the service, test service, that come with a request method of post. If there's a plan that needs these 2 pieces of information, the GTS will tell the gateways, please tell me this. Tell me all the traffic that you see. Then as the traffic arrives in nginx, there's a little bit of logic that just checks for some rules, and in case of a match, it will just let the GTS microservice know about it. And in case something needs to be blocked, GTS sends an HTTP request to all the gateways, like block this application for the next 50 milliseconds. All right, let's switch to see something in action. So what I'm going to show is I have a local setup, which is a test runner, and I'm using JMeter for today so that I simulate more requests. We have this setup with the gateway, the 0MQ adapter. On my machine, they run in the same Docker container. Then I'm also spinning up the tracking service, and I play with the Hello World microservice in the back. We may look into some reporting. GTS pushes some metrics into a Graphite, and they can be visible through Grafana UI. We're going to, once this is spun up, we're going to add a throttling policy. When we had the throttling policy, we built this idea that we can have like 2 watermarks. One of the assumptions was that the intent is not necessarily to block, but rather to be permissive. And we found out that if we can, sometimes if there is a burst, if you manage to delay those requests a little bit, you may be able to fit them into what the service can handle. So we have 2 watermarks. There's a low watermark, which in this case is a soft limit, after which once this limit is reached, the gateway will start delaying the requests. And there's a hard watermark at which requests are blocked. Then we can define rules per different time units. In my example, I'm going to use 10 seconds. And the policies that we implemented are pretty open in the sense that you can use pretty much any variable that is out of the box in nginx, or any variable that you define. In my example, I have a nginx configuration file for my Hello World microservice, and inside of that file, I have a variable which is called service ID. So every request that goes on that virtual host is tracked to be the echo service. So this rule says that when a request hits my echo service, I want to enforce these limits. And we also have this notion of group by. In this case, we're going to limit every single application to a soft limit of 2 requests per 10 seconds and a hard limit of 5 requests per 10 seconds. If it wasn't for the group by, then this limit would have applied for any consumer using this service. There's also an API for deleting a throttling policy and listing a policy. So now let me show you this in action. All right, going to mirror displays. OK. So what I have, I'm going to make an assumption that if I show a Docker compose, we won't freak out too much, and we'll be OK with it. So I have a Docker compose which has the tracking service, the API gateway. It has whatever it needs, the Hello World microservice, the Graphite, and the Grafana. So this is already, I've already started this with Docker compose, and they're running here. Looks like we have a little bit of errors. And now I'm going to start a JMeter test. And in this JMeter test, I'm adding the service plan, as I said. The first service plan that I'm adding is having a hard limit of 12 requests per 10 seconds. And it's applied to the entire echo service. So it doesn't matter if I use 1 application or if I come with 100 applications. It's the same limit. They're all going to be limited at 12. Then I'm going to hit. I have API echo headers RESTful endpoint that just returns the headers back. I have an API key that I'm sending it as a query parameter to identify my application. Maybe this is a similar setup. Sometimes you can extract the API key from an OAuth token or from a different place. Just for the simplicity of the demo, I'm sending it as a query parameter. And then I'm going to run this. So going to hit run. I'm adding these plans into the microservice. And I'm just giving it some times, and then my JMeter is going to start running this test. Everything is OK. We should be throttled after about 12 requests. Not really. Let me try again. Maybe I didn't wait enough. OK. As I said at the beginning, this presentation is about failure. So my demo can fail a little bit, but not too much. All right. So I'm going to destroy my Docker Compose and restart it again. Down. There you go. An unplanned failure during the demo. Thank you for your patience. All right. So let me also clean my thing. OK. Should be fine. Docker Compose. Up. OK. I am going to go into the browser to make sure that the microservice is up. I see that 0MQ is connected. For the microservice is written in Java, and we use a native implementation, which is 0MQ from Java. It performs pretty well. I saw it handling hundreds of thousands of requests per second on the local machine. So that's pretty good. All right, now let's run the test again. And now I've added some throttling plans into my service. Yeah, there you go. Now some applications are, some requests are being blocked, and I think I have about 14 requests. Now, because I set buckets of 10 seconds, again, we're not religious about when do the 10 seconds start. So it just so happens that in the microservice implementation, the 10 seconds is every 10 seconds. So it's not related to when I start the test. So it's possible that when I run the tests, I'm just falling in two windows of 10 seconds, in which case I will have a lot more requests being accepted. But in this case, it looks like everything worked. So what you see in red is something that returned with 4 to 9. Response data is 4 to 9 too many requests. And so this has been blocked by the gateway. What I want to show next, so what we saw so far is that we can implement a hard limit, and we can make this limit available for the entire service. What I want to do next is add an application plan. So I want to make an exception. So just for one application, I want to limit it a little bit more. So the way I can do it is that it's sufficient for me. Can you guys see my screen here? OK, thank you for the confirmation. So besides having the service ID echo service, I've also added API key equals application2. So at this point, this is my domain for my policy. So now if I change the API key into application2, I have a soft limit of 2. After 2 requests, I should start to be delayed, and then a hard limit at 5. So after about 5, I should actually get a 4 to 9 back, so the gateway should reject the calls. So I'm going to run again, add the service plans, but I didn't change the API key. So should get the same response. App1, and it was supposed to be app2. OK, results 3, showing a similar thing as in the previous test. So I'm going to clear this and hit run. So again, I've added a plan which is for the echo service, only for the application2, and I restricted a little bit more. So we should be able to see a change in this. Let's see if it was restricted. Run again, save, and run again, and I have application 2 and API keys application 2. All right, let me run again. These demos, I've been running this, I'm telling you, for 10, 15 times. Never had a problem. Okay. Moving ahead. It's either something that I don't figure it out, or the request is with application 2. Never mind. Please connect with me if you want to see this working. I can show it to you working afterwards. I just don't want to take from your time right now. And the third thing that I wanted to show is that we can also throttle by the HTTP verb. So probably you can imagine that you could have requests that are doing a post or doing uploads, which you want to limit differently than for other requests, which are just simple gets. And those can also be cached. So for in this case, for a request method of post, I'm setting a hard limit of 5. So when I send a post request, I should be throttled much faster. So I'm going to disable this and enable my request, which is I'm doing a post method. And I'm sending pretty much the same number of requests. Hitting run. And then after this runs, I want to show you the difference and the impact between what happens when you what happens if you don't add delay and you're very restrictive and you block traffic, as opposed to what happens if you add a little bit of delay, and what is the impact in the error rate that we see. Yeah. So this demo worked because my application was limited to, let me double check, to 5. So I had a hard limit of 5. And in here, I have 6. Now, the question is, how can I have 6 if I set a limit of 5, right? So if you remember, we wanted to make this asynchronous and non-blocking. So what happened is after the 5th request, that's when we notify the tracking service that the 5th request is passed. And by the time, I don't know, it takes maybe 4 milliseconds, 2 milliseconds for the tracking service to notify the gateway, block this application for the next maybe 9 seconds. The 6th request slipped in. But we said, again, that it's OK to have the assumption. We don't have to be very, very strict. We also have a debug flag into the gateway so that we see if how much time it took for us to validate or to interpret the rules. And we output them as debug headers. So in here, if it's visible all the way to the back, all the requests that have been validated, the response time for the validation is actually 0 milliseconds. And in most of the cases, is like this. If you have very complicated plans, we didn't see that use case. But I imagine if you have a large number of plans and the gateway keeps a list of what it needs to be blacklisted. So if you have a big list, then probably that may add. But we didn't get to that point so far with our traffic. So we do almost 1 billion requests a day, and we have quite a few plans in Adobe. We didn't yet see this case where, because we check a dictionary of blacklisted things, this adds a lot of latency. Most of the times is 0 milliseconds, which means it's sub-millisecond. It's like in nanoseconds. All right, so the last thing I want to show is I want to do a test. I'm going to disable. So in the first test, if you remember, I'm going to run it again. We had a hard limit of 12, and I was hitting with, let me hit with application 1. I was hitting, so I'm going to run this test again. So I don't have any delay in place at all. All I have is after 12 requests in 10 seconds, I want to block the rest. And after 10 seconds, I'm going to allow 12 more, and then I'm going to block, and so forth. It seems to be the case here. Okay, you see that some requests are with black, some with red, and then again with black. It's because I was right in between the two windows of 10 seconds. So at this point, the error rate is like 56%. Let me run it again one last time. And while this executes, I'm going to go and edit this plan, and I'm going to make it so that I will put a soft limit. I'm going to put a soft limit. Let me see, what is the number here? 4 and delay. OK, I'm going to start delaying at 4. And I'm going to say that the max delay period is 3. So what I'm saying here is that after 4 requests, I want to ask the gateway to start delaying. And the delay is somewhere between 3 divided by 2 and 3. That's what the gateway does. It just makes a little bit of random delays in there. So I'm going to click run again. So let's look at the success rate, like the error rate. Error rate is like 78% with only blocking. Okay, and you see we only allowed 12 requests, and or 13 or maybe 14. I don't know exactly. It doesn't look to be 14 here. And now I'm going to show you what happens if we add a delay. I don't want to guess for this demo, so I'll wait for the numbers. And whatever numbers appear, that's what I'm going to say. But I was able to see, okay, let's see what's happening. Usually what we end up doing with these numbers is that we tweak them. So we let the service teams tweak them to the right levels, because it's like a formula which involves how fast the service may reply back with the actual real traffic that you're expecting, the incoming rate. Is it 100 requests per second? Is it 10,000 requests per second? Your rate. If you have like 10,000 requests per second and you want to put a limit of 2 requests per second, but your backend is scaled to 10,000 requests per second, this solution will not actually only let 2 requests. It may let maybe more, because if you have a client that actually uses 10%, if you take 5% of the 10,000, you'll get to a lot more than 2. So usually what the service teams end up doing is that they kind of tweak these numbers to a level of their comfort. So I hope you can see in my screen there's a lot of red in the first case and only some black, which means these requests actually return 200. And if I scroll down with a simple delay, I didn't do much, but I did this in the gateway. You see I have a lot of black things here and some reds. These are like 4 to 9s, too many requests. And the error rate now, it's lower. So it was 78% then, and now it got down to 45%. So that's quite a nice improvement. And again, all we did was just to ask the gateway to delay. And for this demo, I've also added a header, which is X gateway delay. And in this case, we have a delay of 2.5 seconds, again 2.5, 1.5, and so forth. So this would always be between 2.5 and 3, because I had max delay period equals 3. Now, if I were to go back and increase the delay and actually pause the request in the gateway for more than that, I may be able to push more. But this one is pretty nice to observe, and it just builds a pattern where you allow your consumers to use your service, but if they use too much, then you just slow them down a little bit. Some other things that we did with the tracking service have been that because we build this capability in the gateway to basically track and identify some requests, another team in Adobe built a capability to be able to dynamically rewrite them. So instead of blocking or delaying, we did a rewrite. So where this is used is that we may have to put a bug fix, or we may want to test a beta feature, but not for all the users. So what we're doing is that we're telling the tracking service, when you see this request for this user ID, instead of going to this microservice, please take it to the other microservice, because that's my sandbox. And this is happening in production. We don't have to redeploy anything. We just have to send a new policy to the tracking service. It's a pretty used feature. We didn't think of it initially. It's pretty used. What's next for us is that we want to enhance the tracking service and even adjust the limits dynamically and measure by the quality of service instead of having these limits. Like if I give you a service and I give you like 2,000 requests per second, what does that really mean to you? But if I could have a way to measure, for instance, by the response time, so I give you an SLA, or for me, for my service, I want to be able to, or make it to reply within 100 milliseconds, and then it so happens that for reasons that are outside of my control, my microservice just doesn't function well, then I may slow down some of the incoming requests. And also measure by capacity of the service is the third thing, so that instead of, like when there's not so many consumers, but my service is scaled up, allow more traffic if that's possible instead of blocking. That's where we're going. I'm almost out of time. I want to thank you very much for attending this session, and I hope it was useful to you. If there is any questions, I'm happy to take them. If we're out of time, I can stay here and take your questions. More than happy. So once again, thank you very much.